Hello dear students, all of you welcome to Vidyan classes. It is the fourth lecture on relations and functions. Today we will discuss problems on equivalence relation, types of relation and equivalence class. First question, if capital A is the set of A, B, C, D, mention type of relation on A given below. Which of them are equivalence relations? First bit, let R1 be the relation is the set of A order pair, BB order pair, which is same as A order pair, A order pair, A order pair, BB order pair, BB order pair and BB order pair. Since repetition of elements in a set or relation are not allowed, so this set is same as this set. What type of a relation? Mention the type of a relation. This relation is implies as R1 is symmetry and transitive. What is symmetry? What is symmetry relation and transitive relation? R is reflexive on A if for all x belongs to capital A, XX order pair belongs to R. R is symmetric on capital A if XY order pair belongs to R, that implies YX order pair belongs to R. R is transitive, reflexive, symmetry. R is transitive on A if XY order pair belongs to R and YZ belongs to R, that implies XZ belongs to R. R1 is not reflexive. Why? What is the definition of reflexive? For all x belongs to capital A, XS order pair belongs to R. For all x belongs to capital A means x represent A, B, C and D. C belongs to capital A, CC order pair does not belongs to R1. So R1 does not satisfy the definition of reflexive, so R1 is not reflexive. What is the definition symmetric? XY belongs to R, that implies YX belongs to R. Here A order pair belongs to R1, its reverse order pair, that is A order pair belongs to R1, BB belongs to R1, its BB order pair belongs to R1, its reverse order pair, that is BB order pair belongs to R1. So R1 satisfies the definition of symmetric, so it is symmetric. What is transitive? R is transitive on A if XY belongs to R, YZ belongs to R, that implies XZ belongs to R. X related to Y related to Z, X related to Z means that is A order pair belongs to R1. Similarly, X related to Y, Y related to Z, X related to Z, that is BB order pair belongs to R1. So R1 satisfies the definition of a transitive. Therefore, R1 is symmetry and transitive. Clear? Okay. Second bit. Let R2 be the relation which contains A order pair, BB order pair, BB order pair, CC order pair, and DD order pair, which is same as A order pair, A order pair, A order pair, BB order pair, BB order pair, BB order pair, CC order pair, CC order pair, CC order pair. DD order pair, DD order pair, and DD order pair. This set is the same as this set, as repetition of elements in a set or relation are not allowed. Is an equivalence relation since it satisfies the definition of reflexive, symmetric and transitive. For reflexive, A belongs to capital A order pair belongs to R2. So R2 is A belongs to capital A order pair belongs to R2. B belongs to capital A, BB order pair belongs to R2. C belongs to capital A, CC order pair belongs to R2. D belongs to capital A, DD order pair belongs to R2. That means for all X belongs to capital A, X's order pair belongs to R. X represent A, B, C, D. So it satisfies the definition of a reflexive. R2 is also symmetric. What is symmetry? XY order pair belongs to R. That implies YX order pair belongs to R. A order pair belongs to R2. Its reverse order pair, that is A order pair, belongs to R2. BB order pair belongs to R2. Its reverse order pair also in R2. CC order pair belongs to R2. Its reverse order pair, that is CC order pair, belongs to R2. DD order pair belongs to R2. Its reverse order pair also belongs to R2. So it satisfies the definition of a symmetry. Third, transitive. X related to Y, Y related to Z, X related to Z. That means A order pair belongs to R2. Similarly, for B, C and D, we can show R satisfies the definition of transitive. Therefore, R2 is reflexive, symmetric and transitive. That means R2 is an equivalence relation. Equivalence relation means the relation which is reflexive, symmetry and transitive is called an equivalence relation. So R2 satisfies the definition of a reflexive, symmetry and transitive. Hence, R2 is an equivalence relation. Clear? Note down. Next, third bit. Let R3 be the set of AB, BA order pair, BD order pair, and DB order pair. Implies R3 is symmetric since AB order pair belongs to R3, that implies BA order pair belongs to R3. BD order pair belongs to R3, that implies DB order pair belongs to R3. It is the definition of a symmetric. R is symmetric on A if xy belongs to R, that implies yx belongs to R. AB order pair belongs to R3. Its reverse order pair, that is BA order pair, belongs to R3. BD order pair belongs to R3. Its reverse order pair also belongs to R3. So R3 is symmetric. It is a third bit. Fourth bit. Let R4 be the relation which is equal to set of BC order pair, BD order pair, and CD order pair. Is transitive. Since BC order pair belongs to R4, CD order pair belongs to R4, that implies B to C, C to D, that is BD order pair, belongs to R4. It is the definition of transitive. What is transitive? R is transitive on A if xy order pair belongs to R, yz order pair belongs to R, xz order pair belongs to R. R is transitive. Here BC order pair and CD order pair belongs to R4. That implies B to C, C to D, that is BD order pair belongs to R4. So R4 is transitive. Clear? Okay. Fifth bit, R5. A order pair, BB order pair, CC order pair, DD order pair, AD order pair, SC order pair, DA order pair, CA order pair, CD order pair, and DC order pair. R5 represent dash, either reflexive or symmetric or transitive. First test for reflexive. A, B, C, D belongs to capital A order pair, BB order pair, CC order pair, DD order pair belongs to R5. That means for all X belongs to capital A, XS order pair belongs to R5. X means A or B or C or D. So it satisfies the definition of reflexive. So R5 is the replacive. AD order pair belongs to R5. Its reverse order pair DA also belongs to R5. SC order pair belongs to R5. It is reverse order pair, that is CA, belongs to R5. DA order pair belongs to R5. AD order pair also belongs to R5. It is the definition of a symmetry. XY order pair belongs to R, YX order pair belongs to R. R represents symmetry. So R5 is symmetry. Also it is satisfied the definition of a transitive. A to D, D to A. That means X to Y, Y to Z. X to Z, that is A order pair, belongs to R5. Clear? A to A, that is X to Y, Y to Z. X to Z means a D order pair. Also a D order pair is itself is the element in R5. So R5 satisfies in every cases. R5 represent transitive. For example, C to D, C to D, D to A, that is CA order pair. CA order pair itself represent XZ. It is satisfied the definition of replacive, symmetric and transitive. Implies R5 is an equivalence relation on capital A. Since R5 satisfies the definition of replacive, symmetric and transitive. Clear? Okay. Note down. Next question. So that the relation capital R in the set capital A, which is equal to set of X belongs to Z set, so that X greater than equal to 0, less than 12, less than equal to 12, given by R is equal to set of a B order pair, so that mod of A minus B is a multiple of 4, is an equivalence relation. The relation capital R on A is defined by R is equal to set of AB order pair, so that mod of A minus B is a multiple of 4. Mod of A minus B is a multiple of 4, means mod of A minus B is divisible by 4. By the definition of modulus, mod of A minus B is equal to A minus B if A minus B greater than equal to 0. Minus of A minus B if A minus B less than 0. It is the definition of a modulus. Implies mod of A minus B is equal to plus or minus of A minus B if A minus B belongs to real set. Clear? A minus B greater than equal to 0, A minus B less than 0. That means A minus B belongs to R. So the relation can be written as, so R is equal to set of AB order pair, so that plus or minus a minus b is a multiple of 4, which is same as AB order pair such that m plus or minus a minus b is equal to 4k. That is a minus b is equal to plus or minus 4k for some integer k. Modulus of a minus b is the same as plus or minus of a minus b. So R is equal to set of a b order pair such that plus or minus a minus b is a multiple of 4 or which is same as plus or minus a minus b is equal to 4k. That means 4k is divisible by 4 or a minus b is equal to plus or minus of 4k for some integer k. We have to test the relation EG reflexive, EG equivalence. That means the relation satisfies the definition of reflexive, symmetry and transitive. Let ABC belongs to A. Test for reflexive. Test for reflexive. For all A belongs to capital A minus B is equal to plus or minus of 4k, where k belongs to Z set. A minus A is equal to 0, which is same as 4 into 0. That is 0 is the multiple of 4. That is 0 is the multiple of 4. Implies this A order pair belongs to R. So for all A belongs to A order pair belongs to R. Therefore, R is reflexive. Since for all A belongs to capital A order pair belongs to R, therefore R is reflexive. Clear? That means A minus A is a multiple of 4 or divisible by 4. For all A belongs to capital A minus A equal to 0, which is same as 4 into 0. That is A minus A is divisible by 4. Clear? So the relation is reflexive. Symmetric. Test for symmetric. AB belongs to R so that modulus of A minus B is a multiple of 4. That means A minus B is equal to 4k. So that A minus B is equal to 4k. A belongs to Z set, which implies this B minus A is equal to A minus B is equal to plus or minus of 4k. A minus B is equal to plus or minus of 4k. B minus A is equal to minus plus 4k. Clear? Which implies as minus plus 4k means b minus a is the multiple of 4. BA order pair belongs to R. Now we have AB order pair belongs to R. That implies BA order pair belongs to R. AB order pair belongs to R. That implies BA order pair belongs to R. It is the definition of a symmetry. So R is a symmetry. Clear? Clear? Okay. Next, transitive. AB order pair belongs to R and BC order pair belongs to R, so that AB order pair belongs to R. That implies A minus B is equal to plus or minus 4k. Implies so that A minus B is equal to plus or minus 4k1. And B minus C is equal to plus or minus 4k2. That means A minus B is a multiple of 4, B minus C is a multiple of 4, k1, k2 belongs to Z set, which implies as A minus B plus B minus C is equal to plus or minus 4 k1 plus k2 which is equal to plus or minus 4 k3, which implies as A minus C dt cancel is equal to plus or minus 4 k3. A minus C is a multiple of 4. A minus C is a multiple of 4, which implies as A C order pair belongs to R. AB order pair belongs to R if AB order pair belongs to R if A minus B is a multiple of 4, that means A minus B is equal to plus or minus of 4k. Here A minus C is a multiple of 4, implies SC order pair belongs to R. Now we have AB order pair belongs to R, BC order pair belongs to R, that implies SC order pair belongs to R. It is the definition of transitive. Therefore, R is transitive. Now we have R is reflexive, R is reflexive, R is symmetric, and R is transitive. Since R is reflexive, symmetric, and transitive, implies R is on equivalence relation on A. Hence proved. The first part is proved. So that R is an equivalence relation. Since R is reflexive, symmetric and transitive, implies R is an equivalence relation on A. Hence proved. Second part, find the set of all elements related to 1. The relation is given by modulus of A minus B is a multiple of 4, or the difference of A and B is equal to plus or minus of 4k. That means A minus B is a multiple of 4. Second part, find the set of all elements related to 1. Set up, let B be the set. Collection of, that means collection of all elements whose difference from 1 is a multiple of 4. Find the set of all elements related to 1. We have to collect the elements whose difference by 1 is a multiple of 4. Since modulus of A minus B is a multiple of 4, that means the difference is a multiple of 4. So the collection is, let B be the set related to 1. 1 minus 1, that is 0, is a multiple of 4. 5, 1 minus 5 or 5 minus 1 is a multiple of 4. 1 minus 5 is minus 4. 5 minus 1, that is plus 4. 4 and minus 4 are multiple of 4. And which belongs to A. 1, 5, multiple of 4. Difference is multiple of 4. The next number is 9. 9 minus 1 is 8, or 1 minus 9, that is minus 8, is a multiple of 4, is the required set. Find the set of all elements related to 1. That means find the set whose elements and the difference of 1 and the elements of B, which is a multiple of 4. So B is the required set which contains 1, 5 and 9. Clear? Next question. Let capital N be the set of natural numbers and R be the relation on n cross n defined by AB order pair related to CD order pair if and only if AD is equal to BC for all A, B, C, D belongs to capital N, so that R is an equivalency relation. Solution. Given R is a relation on n cross n. R is a relation on n cross n and defined by AB order pair related to CD order pair. AB order pair if and only if AD is equal to BC. Given R is a relation on n cross n and defined by AB order pair related to CD order pair if and only if AD is equal to BC. AD is equal to BC. If AD is equal to BC, then AB order pair related to CD order pair. Clear? We have to show the relation R is equivalence. That means R satisfies the definition of replacive, symmetric and transitive. Let AB order pair, CD order pair, EF order pair belongs to n cross n. Cartesian product contains the coordinate points or order pairs where A, B, C, D, E, F belongs to capital N. That means A, B, C, D, E, F are natural numbers. Test for reflexive. For all AB order pair belongs to n cross n. For all AB order pair belongs to n cross n, AB order pair related to AB order pair as AB is equal to BA, as AB is equal to BA. That is multiplication is commutative on n. Multiplication is commutative, AB is equal to BA. That means multiplication is commutative on the set of natural numbers. Clear? So, the relation R is reflexive. For all AB belongs to n cross n, AB order pair related to AB order pair as AB is equal to BA, AB is equal to BA since multiplication is commutative on the set of natural numbers. It is the definition of reflexive. So the relation R is reflexive. Test for symmetry. AB order pair related to CD order pair implies an implicit pair. That means if and only if AD is equal to BC, which implies BC is equal to AD, which implies we have to show CD order pair. CD order pair related to AB order pair. CB, and this is same as CB is equal to DA. BC is same as CB, AD is same as DA. That implies as CB and DA are equal, we can write CD order pair related to AB order pair. Now we have AB order pair related to CD order pair implies a CD order pair related to AB order pair. Therefore, R is symmetric. X related to Y, that implies Y related to X, so that R is symmetric. Here, AB order pair related to CD order pair, CD order pair related to AB order pair, so the relation defined by is symmetric. Test for transitive. Test for transitive. AB order pair related to CD order pair and CD order pair related to EF order pair. AB order pair related to if and only if implied and implied by AD is equal to BC and CF is equal to D, which implies this. C by D is equal to A by B. BC is equal to AD and C by D is equal to E by F. DE is equal to CF, which implies this. C by D is equal to A by B, C by D is equal to E by F. So that implies A by B is equal to E by F, which implies this. AF is equal to BE, which implies this. AF is equal to BE. AB order pair is equal to EF order pair. AF order pair is equal to B order pair. Now we have AB order pair related to CD order pair and CD order pair related to EF order pair. That implies AB order pair related to AB order pair related to AB order pair related to EF order pair. AB order pair related to CD order pair, CD order pair related to EF order pair. That implies AB order pair related to EF order pair. It is the definition of a transitive. Clear? It is the definition of a transitive. So R is transitive. Clear? Since R is reflexive, symmetric and transitive on encroachment implies R is on equivalence relation on n cross n. Hence proved. Clear? Okay. Next question. Show that the relation capital R in the set containing 1, 2, 3, 4, 5 and 6 defined as R is equal to set of AB order pair such that B is equal to A plus 1 is neither reflexive nor symmetric nor transitive. Solution. Let capital X be the set containing 1, 2, 3, 4, 5 and 6. The relation capital R on X is defined by R is equal to set of AB order pair so that B is equal to A plus 1. AB order pair belongs to R if B is equal to A plus 1. B is equal to A plus 1. For A is equal to 1 implies this B is equal to 1 plus 1, that is 2. A is equal to 2 implies this B is equal to 3. A is equal to 3, B is equal to 4. A is equal to 4, B is equal to 5. A is equal to 5, B is equal to 6. A is equal to 6 implies this B is equal to 7 not belongs to X. So there exist 5 order pairs in R. So R is equal to set of 1, 2, 2, 3 order pair, 3, 4 order pair, 5, 4, 5 order pair, 5, 6 order pair. There exist 5 elements in R. We have to show the relation defined by is neither reflexive nor symmetric nor transitive. Reflexive. Test for reflexive. 1 belongs to, what is the definition of reflexive? For all X to the given set, X's order pair belongs to R. Here 1 belongs to capital X, but 1 order pair does not belongs to R. 2 belongs to capital X, but 2 order pair does not belongs to R. Similarly, we can show for other elements. That is 6. 6 belongs to capital X, but 6 order pair does not belongs to capital R. For all X to the given set, X's order pair belongs to R, then the relation R is said to be reflexive. Here 1 belongs to capital X, 1 order pair does not belongs to R, 2 belongs to capital X, 2 order pair does not belongs to R, Similarly, we can test for other elements. Last number, that is 6, belongs to capital X, but 6 is odd pair, does not belongs to R. So R is not reflexive. Test for symmetry. The relation R is said to be symmetric if xy order pair belongs to R, that implies yx order pair belongs to R. Here 1 2 order pair belongs to R, 1 2 order pair belongs to R, but 2 1 order pair does not belongs to R. 2 3 order pair, 2 3 order pair belongs to R, but 3 2 order pair does not belongs to R. Clear? Does not belongs to R. xy belongs to R, that implies yx belongs to R, then R is symmetric. It does not satisfy the definition of symmetry. So R is not symmetric. Clear? Test for transitive. What is the definition of a transitive? The relation R on X is said to be transitive if xy belongs to R, yx belongs to R, that implies xz belongs to R. 1 2 order pair belongs to R, 2 3 order pair belongs to R, but x related to y related to z, x related to z means 1 3 order pair does not belongs to R. 1 3 order pair does not belongs to R. Similarly, we can show for other elements. Therefore, R is not transitive. R is not reflexive. R is not symmetric. R is not transitive. In general, the relation defined by is neither reflexive nor therefore, in general, the relation defined by is neither reflexive nor symmetric nor transitive. Hence, proved. Clear? Clear? Okay. Note down. Next question. So that the relation capital R in the set of real numbers defined as R is equal to set of AB order pair so that A less than or equal to B square is neither reflexive nor symmetric and transitive. Given R is the relation on real set R is the relation on R defined by R is equal to set of AB order pair so that A less than or equal to B square. AB order pair belongs to R so that A less than or equal to B square. For A belongs to real set, A less than equal to A square implies A square minus A greater than equal to 0. Here, for A belongs to R, A less than or equal to A square. For A belongs to R, so that A less than or equal to A square. That implies A square minus A greater than or equal to 0, which is same as A into A minus 1 greater than or equal to 0. It is A is equal to 0, it is B, A is equal to 1. There exist 3 intervals. This interval A greater than or equal to 1. In this interval, A into A minus 1 is 0 or positive. It is 0 or positive. Since it is positive, it must be negative. A greater than 0, less than 1. For A greater than 0, less than 1, it is negative. And it is positive. A less than or equal to 0. Implies A into A minus 1 greater than or equal to 0 implies A belongs to open bracket minus infinity to 0 union in this interval A into A minus 1 greater than equal to 0. In this interval A into A minus 1 greater than equal to 0. 1 to infinity, which is not equal to R. R means minus infinity to plus infinity. A less than equal to A square is true when A belongs to this set. A belongs to this set, but this set is not equal to R. We have to test the relation is replacive, or we have to show it is neither replacive nor symmetric nor transitive. Test for reflexive. Clear? For all A belongs to R, that is a real set, A square A less than equal to A square, that is for all A belongs to real set A less than equal to A square, that is A square minus A greater than equal to 0 is not true always. For all A square minus greater than equal to 0 when A belongs to this interval. It is not true in real set. For all A belongs to R, that is real set, A less than equal to A square, that is A square minus A, is not true always. Implies this. A less than equal to B square. A B order pair belongs to R. Here A equal to B. A order pair does not belongs to R. For all A belongs to real set, A order pair does not belongs to R. E.g. A order pair does not belongs to R. For example, A is equal to half. A less than equal to A square, that means half less than 1 by 4 is not true. For all A belongs to capital R, that is real set, A order pair does not belongs to R. Therefore, R is not reflexive. Clear? A less than equal to A square is true when A belongs to this set, not R. Here, for all A belongs to real set, A less than equal to A square is not true always. It is true in this set and in this set. A less than equal to A square implies A order pair does not belongs to R. So, for all A belongs to R, A order pair does not belongs to R. It does not satisfy the definition of reflexive. Therefore, R is not reflexive. Clear? Okay. Test for symmetry. A B order pair belongs to R, so that A less than equal to B square. But it's symmetric. A B order pair belongs to R. That implies BA order pair belongs to R. So that the relation is symmetric. That implies B less than equal to A square is not true always. For example, A is equal to 3, B is equal to 10. A less than 10, A less than equal to B square. Is it true? But B less than equal to A square. B means 10. 10 less than equal to 9 is not true. Clear? A less than equal to B square. A B order pair belongs to R. That implies A less than or equal to B square. Implies this B less than equal to A square is not true always. When A is equal to 3, B is equal to 10, it does not satisfy. B less than equal to A square implies this. BA order pair does not belongs to R. Now we have AB order pair belongs to R, but BA order pair does not belongs to R. Therefore, R is not symmetric. R is not reflexive, R is also not symmetric. Test for transitive. Test for transitive. What is the definition of a transitive? AB order pair belongs to R, BC order pair belongs to R, that implies AC order pair belongs to R, so that R is a transitive. ABC belongs to R, real set. For symmetric, AB order pair, AB belongs to R. AB belongs to R, real numbers. AB order pair belongs to R and BC order pair belongs to R, so that A less than equal to B square. Since AB order pair belongs to R, A less than equal to B square, and BC order pair belongs to R, B less than equal to C square. Clear? Which implies this A less than equal to B square and B square less than equal to C fourth. Combining the above, we have A less than equal to B square, B square less than equal to C to the power 4, implies this A less than equal to C to the 4 is not true always. Also, A less than equal to C square is not true always. For example, A is equal to 1 by 3, B is equal to minus 3, and C is equal to minus 1 by 3, implies this A less than equal to B square. A is 1 by 3, B square means 9. 9 greater than 1 by 3, 2. And B square, B less than equal to C square. B means minus 3, C square means 1 by 9, 1 by 9 greater than minus 3 are true always. But A less than equal to C square. A means 1 by 3. C means 1 by 9 is not 1 by 3 less than or equal to 1 by 9 is not true. Is not true. A less than equal to C square is not true always. Implies AC order pair does not belongs to R. Now we have AB order pair belongs to R, BC order pair belongs to R, but AC order pair does not belongs to R. Therefore, R, it does not satisfy the definition of a transitive. Therefore, R is not transitive. In general, the relation capital R defined on real set is in general the relation capital R defined on real set is neither reflexive nor symmetric and nor transitive. Hence proved. Clear? Clear? Okay. Note down. Not reflexive, not symmetric, not transitive. Note down. Next question. So that the relation R in the set of real numbers defined as R is equal to set of AB order pair so that A less than or equal to BQ is neither reflexive nor symmetric nor transitive. Same question. Solution. The relation R on real set is defined by R is equal to set of AB order pair so that A less than or equal to BQ. A less than or equal to BQ. For A belongs to real set. So that A less than or equal to AQ. That implies AQ minus A greater than equal to 0. Which is same as A into A square minus 1 greater than or equal to 0. Which implies A into A minus 1 into A plus 1 greater than or equal to 0. A is equal to 1, A is equal to 0, A is equal to minus 1. For A greater than equal to 1 in this interval, suppose A equal to 2, this value is positive. At A equal to 1, the value is 0. So it is a positive interval. A greater than equal to 1. If it is positive, then it will be negative. A greater than 0, less than 1. The neighboring interval is positive. A greater than minus 1, less than 0. Or less than A greater than 0, less than equal to 0. And it is the negative interval. A less than or equal to minus 1. A greater than minus 1, less than 0. A into A minus 1 into A plus 1 greater than or equal to 0. So, A less than or equal to AQ implies A belongs to, it is the positive interval, it is the positive interval. Close bracket, -1 to 0, close bracket. A less than equal to -1, A greater than equal to -1. Union A 1 to infinity. At A equal to 1, the value is 0. At A equal to 0, the value is 0. At A equal to -1, the value is 0, which is not equal to real set. A less than equal to AQ when A belongs to this, not belongs to R. We have to test. The relation is not replacive, not symmetric, and not transitive. Reflexive. For all A belongs to R, A less than equal to AQ is not true always. Implies A order pair does not belongs to R. For example, A is equal to 1 by 3. A less than equal to AQ is not true. Clear? A less than or equal to AQ is true in this interval and in this interval. It is not true for every real number. For example, A is equal to 1 by 3, A less than or equal to AQ is not true. So R is not reflexive. Clear? Clear? A less than or equal to AQ is true when A belongs to this set or this set, not in R set. Clear? No doubt? Clear? For symmetric. Every order pair belongs to R, so that A less than or equal to BQ. Every order pair belongs to R, so that A less than or equal to BQ. Implies B less than equal to AQ is not true always. For example, A is equal to 1, B is equal to 2. A less than or equal to BQ is true. But B less than equal to AQ, B is 2 and A is 1. 1 greater than 2 is not true. Not true. implies BA order pair does not belongs to R. AB belongs to R, but BA does not belongs to R. Since AB belongs to R, but BA does not belongs to R, implies R is not symmetry. R is not reflexive and R is not symmetry. Clear? No doubt? No doubt? Okay. Transitive. AB order pair belongs to R. BC order pair belongs to R. So that A less than equal to BQ and BC belongs to R. And B less than equal to CQ, which implies A less than equal to BQ and BQ less than equal to C to the power 9. A less than equal to BQ less than equal to C to the power 9 is not true always. Also, A less than equal to CQ is not true always. For example, A is equal to 10, B is equal to 3, C is equal to 2. A less than equal to BQ. A less than equal to BQ. EG and B less than equal to CQ are true always. But A less than equal to CQ, that is 10 less than 8, is not true. Now we have implies AC order pair does not belongs to R. AB order pair belongs to R, BC order pair belongs to R, but SC order pair does not belongs to R. Now we have AB order pair belongs to R, BC order pair belongs to R, but SC order pair does not belongs to R. Therefore, R is not transitive. Clear? AB belongs to R implies A less than equal to BQ. BC order pair belongs to R, B less than equal to CQ, A less than equal to BQ and BQ less than or equal to C to the power 9. taking whole cube both the sides, which implies this a less than equal to b cube less than equal to c to the 9 is not true always. Also a less than or equal to c cube is not true always. For example, a is equal to 10, b is equal to 3, c is equal to 2. A less than equal to bq is true. Since a is 10, bq means 27. B less than equal to cq, b is 3, cq means 8. A less than equal to bq and b less than equal to cq are always true. But a less than equal to cq, that means 10 less than or equal to 8 is not true. AB belongs to AB order pair belongs to R, BC order pair belongs to R, but SC order pair does not belongs to R. So the relation is not transitive. In general, R is not replacive in general. R is neither reflexive nor symmetric nor transitive. In general, R is neither reflexive nor symmetric nor transitive. Hence proved. R is not reflexive, R is not symmetric, R is not clear. Note down. Okay. Next question. Let R be the relation in the set containing 1, 2, 3, 4 given by R is dash type relation. Answer. R is equal to set of 1, 2, 2, 2 order pair, 1, 1 order pair, 4, 4 order pair, 1, 3 order pair, 3, 3 order pair, 3, 2 order pair, which is same as 1, 2 order pair, 2, 2 order pair, 1, 1 order pair, 4, 4 order pair, 1, 3 order pair, 3, 3 order pair, 3, 2 order pair, 1, 2 order pair, 1, 3 order pair, and 3, 2 order pair. 1, 2 order pair, 1, 3 order pair, 3, 2 order pair is repeated twice. Repetition of elements in a relation or set are not allowed. So this set is same as this set. Test for reflexive. What is the definition of reflexive? For all x to the given set, excess order pair belongs to R. For all x to the given set, let A be the set containing 1, 2, 3, 4. For all x to the given set means x represent 1, 2, 3 and 4. 1 belongs to A, 1 order pair belongs to R. 1 order pair belongs to R. 2 belongs to A, 2 order pair belongs to R. 3 belongs to A, 3 order pair belongs to R. 4 belongs to A, 4 order pair belongs to R. 1 order pair, 2 order pair, 3 order pair, and 4 order pair belongs to R. Implies this. R is the reflexive. Here, for all x to the given set, that is capital A, excess order pair belongs to R, that means 1 order pair belongs to R, 2 order pair belongs to R, 3 order pair belongs to R, 4 order pair belongs to R, since the set contains 1, 2, 3, 4. Test for symmetry. What is the definition of symmetry? XY order pair belongs to R, that implies YX order pair belongs to R. R contains 1, 2. 1, 2 order pair belongs to R. But 2, 1 order pair does not belongs to R. 1, 2 order pair belongs to R. There is no element in R containing 2, 1 order pair. Similarly, 1, 3 belongs to R, but 3, 1 does not belongs to R. 3, 2 belongs to R, but 2, 3 does not belongs to R. So, R is not symmetric. Clear? XY order pair belongs to R, but YX order pair does not belongs to R. Test for transitive. Transitive. What is the definition of a transitive? XY order pair belongs to R, YZ order pair belongs to R, that implies XZ belongs to R. 1, 2 order pair belongs to R, 2, 2 order pair belongs to R, that implies 1, 2 order pair belongs to R. X to Y, Y to Z, X to Z means 1, 2 is present. So it is the transitive. Similarly, 1, 2, 1. 1, 2, 1. 1, 1 order pair belongs to R. 1, 3 order pair belongs to R. Implies this 1, 3 order pair belongs to R. X to Y, Y to Z, X to Z means 1, 3 is present in R. 1, 3, 3, 3, that is 1, 3. 1, 2, 3, 3, 2, 1, 2, 3. Similarly, 1, 2, 3, 3, 2, 3, 1, 3, that is 1, 3 present in this. 3, 2, 3, 3, 2, 2, 3, 2, 3, 3, 2, 2, that is 3, 2 belongs to this. Similarly, we can test for other elements. Similarly, we can show for other elements satisfying the definition of transitive. Clear? Therefore, R is the transitive. In general, R is reflexive, R is transitive, but R is not symmetric. R is reflexive, symmetric, but not, R is reflexive, transitive, but not symmetric. Clear? Clear? Okay. Note down. Next question. Let capital R be the relation in the set of natural numbers given by R is equal to set of AB order pair so that A is equal to B minus 2, where B greater than 6. Choose the correct answer from ABCD. Solution. AB order pair belongs to R so that A is equal to B minus 2 where B greater than 6 implies B is equal to A plus 2. For A is equal to 2, it is A, it is B, it is A, it is B. A is equal to 2 implies B is equal to 4. 2 plus 2. Not true since B greater than 6. A is equal to 3, B is equal to 2 plus 3, that is equal to 5. Not true since B is greater than 6. A is equal to 6, B is equal to 8. Is it true? A is equal to 8, B is equal to 10. So the correct option is 6, 8. For A is equal to 8, B is greater than 6, but there is no order pair in R. For A is equal to 8, it is given 7, but B is, therefore C 6, 8 belongs to R. Is correct. Note down. Note down. Okay. Next question. Let capital R be a relation on X. If R is symmetric, then X related to Y, that implies Y related to X. If it is also transitive, then X related to Y and Y related to X, that implies X related to X. So, whenever a relation is symmetric and transitive, then it is also reflexive. What is the wrong in this argument? What is the wrong in this argument? X related to Y, that implies Y related to X. It is the definition of a symmetry. So, R is symmetry. X related to Y and Y related to X. That means X related to Y, Y related to Z, Z means X, X related to X, that is X related to X. So, it satisfies the definition of a transitive. Whenever a relation is symmetric and transitive, then it is also reflexive. X related to X is not the definition of reflexive. R is reflexive if X related to X for all X to the given set. So, X related to X is the wrong argument in this statement. Solution. x related to x is the wrong argument in this statement. Since by definition R is reflexive on capital X if x related to x for all x belongs to capital X. Here x related to x is present, but for all x belongs to capital X is not present. Clear? For example, let R be a relation on capital X is the set containing 1, 2, 3. R is equal to set of 1 order pair, 2 order pair, 1 2 order pair, 2 1 order pair, which is same as 1 1 order pair, 1 1 order pair, 1 1 order pair, 2 2 order pair, 2 2 order pair, and 2 2 order pair, 1 2 order pair, and 2 1 order pair. This is same as this set, since repeated elements in a relation or set are not allowed. 1 1 order pair is repeated thrice, 2 2 order pair is repeated thrice. So that R satisfies the definition of symmetric and transitive. 1 1 order pair present, its reverse order pair, that is 1 1 order pair is present. 2 2 order pair present, its reverse order pair also present, that is 2 2 order pair. 1 2 order pair present, its reverse order pair 2 1 order pair is present in R. Or we can say 2 1 order pair belongs to R, its reverse order pair, that is 1 2 order pair belongs to R, so it is satisfies the definition of a symmetry. Also it is satisfies the definition of a transitive. X related to y, y related to z, x related to y, y related to z, x related to z means that is 1 1 order pair belongs to R. 2 2 order pair belongs to R, 2 2 order pair belongs to R, that means x related to y, y related to z, x related to z means 2 2 order pair belongs to R, it satisfies the definition of a transitive. Similarly, we can show for other elements. For example, x related to y, y related to z, x related to z means 1 1 order pair is present in R. Clear? 2 2 order pair belongs to R, 2 1 order pair belongs to R. That means x related to y, y related to z, x related to z means 2 1 order pair is also present in this. We can write 1 2 2 1. X related to y, y related to z, x related to z, that is 2 1 order pair belongs to R. It is satisfies R satisfies the definition of definition of symmetric and transitive. But R is not reflexive. Since X contain 1, 2, 3. 3 belongs to capital X. But 3 order pair does not belongs to R. R will be reflexive if for all X to the given set, XS order pair belongs to R. 1 belongs to capital X, 1 order pair present. 2 belongs to capital X, 2 order pair belongs to R. But 3 belongs to capital X, 3 order pair is not belongs to R, so it is not reflexive. Clear? X related to X is the wrong argument in this statement, since by definition R is reflexive on X if XS order pair X belongs to R or X related to X for all X belongs to capital X. Clear? It is the example of the argument. Note down. Okay. Next question. Write all equivalence relations on capital X is a set containing ABC. Equivalence relation means the relation which is reflexive, symmetric and transitive. R1 is the set of A order pair, BB order pair, CC order pair. Is the smallest equivalence relation on X. R2 is the set of A order pair, BB order pair, CC order pair, AB order pair, BA order pair. R3 A order pair, BB order pair, CC order pair, BC order pair and CB order pair. R4 A order pair, BB order pair, CC order pair, SC order pair, CA order pair. R5 that is A cross A. X cross X. The given set is X. X cross X, which contains A order pair, BB order pair, CC order pair, AB order pair, BA order pair, BC order pair, CB order pair, SC order pair, and CA order pair is the largest equivalence relation on capital X. Write all equivalence relations on X. Therefore, R1, R2, R3, R4, and R5 are the equivalence relations. All equivalence relations are all equivalence relations. R1, R2, R3, R4 and R5 are all equivalence relations on X. Since R1, R2, R3, R4 and R5 satisfies the definition of reflexive symmetry and transitive. R1, R2, R3, R4 and R5 satisfies the definition of a reflexive symmetry transitive. R1 is the smallest equivalence relation on X. R5, that is X cross X, is the largest equivalence relation on X. Clear? Clear? Okay. No doubt? Next, partition of set. What is a partition? Definition: let capital A not equal to 5 means A is a non-empty set. P is the set of P1, P2, P3 Pn. Capital A is a non-empty set. Capital P is the set of P1, P2 Pn with the set of all non-empty subsets of capital A. A is a non-empty set. P is the set of all non-empty subsets of capital A. Capital P is called partition of A. If First condition, A is equal to P1 union P2 union P3 dot union Pn, which is same as I varies 1 to n over union of Pi. That means union I varies 1 to n over union Pi means P1 union P2 union P3 dot Pn, whose union is equal to A set. Second condition, Pi intersection Pj is equal to phi, where I varies 1, 2, 3 up to n, j varies 1, 2, 3 up to n, but I not equal to j. If these two conditions are satisfied, then P is equal to the partition of A. A is non-empty, P the set of all non-empty subsets of A. P is equal to partition of A if P1 union P2 union P3 dot Pn is equal to capital A. Or we can say I varies 1 to n over union of Pi is equal to A. Intersection of any Pi and Pj is equal to phi. Intersection is phi, where I varies 1 to n, j varies 1 to n, but I not equal to j. Example, let capital A be the set of 1, 2, 3, 4, 5, 6. P is the set of 1, 2, 3, 4, 5 and 3, 6. Each P a partition of capital A. A is the set of 1, 2, 3, 4, 5, 6. P is the set of 1, 2, 3, set of 4, 5, set of 3, 6. Each P a partition of A. Solution. No. Region intersection of set of 1, 2, 3 intersection of set of 3, 6 is equal to set of 3, not equal to 5. That is the second condition is not satisfied. Intersection of any two Pi is equal to null set. Union is a set, but intersection is intersection of Pi and Pj, where I not equal to j. This and this, whose intersection is equal to set of 3, is not equal to 5. Clear? Okay, note down. Next, equivalence class. What is equivalence class? What is the definition? let small a belongs to capital A and R be the equivalence relation on A. Let A belongs to capital A and R be the equivalence relation on A. The equivalence class of small a is written as bracket of A and defined by equivalent class of A is the collection of X so that Ax belongs to R. It is also denoted by equivalent class of A on R, where R is the equivalence relation. Let capital A, small a belongs to capital A and R with the equivalence relation on capital A. The equivalence class of A is written as bracket of A or bracket of A on R for R and defined by equivalent class of A is the collection of X so that A and X are related. Clear? Equivalent class is a set whose element is X. A and X are related. That means Ax belongs to R, where R is the equivalence relation on capital A. Example, find all equivalence classes of the find all equivalence classes of the equivalence relation capital R is the set of A order pair, BP order pair, CC order pair on A is the set of ABC. Find all equivalence classes of the equivalence relation which contains A order pair, BB order pair and CC order pair on capital A is the set containing small a, b, c. What is equivalence class? It is the definition of equivalent class. Solution. Equivalence class of A which is same as equivalent class of A on the equivalence relation for the equivalence relation R is defined by the collection of X so that Ax belongs to R. Equivalent class of A for the equivalency relation R is the collection of X so that Ax are related. That means Ax order pair belongs to R, where R is the equivalency relation on set of ABC. R is equal to A order pair, BB order pair, CC order pair, A order pair belongs to R. A order pair belongs to R. The definition of equivalent class is the collection of X, so that A related to X. A order pair belongs to R. R is the equivalency relation. A related to A. So equivalent class of A is the collection of X on R, or simply written as equivalent class of A. A related to A. A related to A. A related to X, the collection is X. A related to A, so the collection that is set is A. BB order pair belongs to R. Equivalent class of B, B related to B. Here the X is B. So equivalent class of B or equivalent class of B for the equivalency relation R is the collection of B. Clear? CC order pair belongs to R. So equivalent class of C or equivalent class of C for the equivalency relation R, the collection is X. Here X related to X. X related to C. X means C. So equivalent class of C for the equivalency relation R is the set of C. Clear? Set of A, set of B, set of C are three equivalence classes of and all equivalent classes of the equivalency relation. Find all the equivalence classes for the equivalency relation R. Find all equivalent classes for the equivalency relation this. Equivalent class of A, equivalent class of B, equivalent C are three equivalent classes for the equivalence relation R. For the equivalency relation R. Note. Set of A union set of B union set of C is equal to set of ABC is equal to A. There are three equivalence classes for the equivalency relation R. Second, equivalent class of A intersection equivalent class of B. Equivalent class is a set. is equal to phi. That is equivalent class of A intersection equivalent class of B is equal to phi. Equivalent class of B intersection C also phi. It is equivalent class of A, it is equivalent class of B, it is equivalent class C. Union is A set, intersection is phi set. Equivalent class of C intersection equivalent class of A is also phi set. R is the equivalency relation which decomposes the given set into disjoint equivalent classes. Clear? Second example. Example 2. Find all equivalence classes for the equivalence relation are A order pair, BB order pair, CC order pair, AB order pair, and BA order pair. Find all equivalence classes for the equivalence relation R, which is the set of A order pair, BB order pair, and CC order pair, AB order pair, BA order pair. In previous question, we have discussed this and this and this are two equivalence relations on A is equal to set of ABs. Answer or solution: equivalent class of A on which is same as equivalent class of A for the relation equivalence relation R is defined by collection of X so that AX belongs to R. Clear? A order pair belongs to R. Suppose it is R1. A related to equivalent class of A is the collection of X. AX order pair belongs to R. Here X is given by A. So the set is A order pair belongs to R1. R1 is the equivalence relation. So equivalent class of A. Here the X is A. BB order pair belongs to R1. Also A order pair belongs to R1. A order pair belongs to R1. AB order pair belongs to R1 implies equivalent class of A. Here X takes value A and B. So equivalent class of A for the equivalence relation R1 is the set of AB. X is A, X is B. BB order pair belongs to R1. BA order pair belongs to R1 implies equivalent class of B for the equivalency relation R1 is the collection of here X is B and A and B. So equivalent class of A is same as equivalent class of A is same as equivalent class of B. So equivalent class of A is same as equivalent class of B is equal to set of AB. CC order pair. CC order pair belongs to R1. So equivalent implies equivalent class of C, which is same as equivalent class C for the equivalency relation R1 is the set of C. Clear? Here X takes value C. Equivalent class C is C. From the above discussion, it is clear that equivalent class of set of AB, set of C, that means equivalent class of A is the same as equivalent class of B and equivalent class of C is the set of C are two equivalence classes of equivalent class of A is the set of AB and equivalent class of C is the set of C are the equivalent classes for the relation R1. This and this are two equivalence classes for the equivalency relation R1. Note union of set of AB and the set of C is equal to A set. That is equivalent class of A union equivalent class of C is equal to A. Equivalent class of A is the same as or equivalent class of A is the same as equivalent class of A is same as equivalent class of B. Union equivalent class C is equal to A. And since equivalent class of A is the same as equivalent class of B and equivalent class of A intersection equivalent class of C, equivalent class of A contains set of AB, equivalent C contains C. There is no common element, so it is phi. Equivalent from this discussion, it is clear that equivalence relation decomposes the given set into disjoint equivalent classes. Clear? Here the equivalence relation R decomposes the given set into three equivalent classes. Here R1 is the equivalence relation decomposes the given set A into two equivalence classes. Note equivalence relation decomposes or partitions the given set into disjoint equivalence classes. Clear? Equivalence relation. Here R is the equivalence relation. Decomposes the given set, that is a set of ABC, into three equivalent classes whose union is a given set and intersection of any two is a phi set. Here also the equivalence relation R1 decomposes or partitions the given set, that is A, capital A, into two equivalence classes. The two equivalent classes are set of AB and set of C, whose union is the given set, that is capital A, and intersection is the phi set. In general, we can say equivalence relation decomposes or partitions the given set into disjoint equivalent classes. Note 1. These are the properties of the equivalence classes. A belongs to equivalent class of A. Clear? A belongs to equivalent class of A. B belongs to equivalent class of B. C belongs to equivalent class. In general, we can say A belongs to equivalent class of A. Third, equivalent class of A is equal to equivalent class of B implies and implied by A related to B, where R is the equivalence relation. Two equivalence classes are disjoint to each other or identical to each other. These are the properties of the equivalence classes. Equivalence relation decomposes or partitions of the given set into disjoint equivalence classes. A belongs to equivalent class. From this property, it is clear equivalent class of A is equal to equivalent class of B, that implies and implied by A related to B. That means two equivalent classes are identical to each other or disjoint to each other. Clear? Note down.